Good morning, everyone. Alright, so time to break this food. Alright, so I will start off by looking at the grading optimizer. So my fellow colleagues have been looking at workflows, integration of data management between software applications, and so we'll be actually looking at how do we integrate AI tools within the application itself when it comes to the actual design efforts. So before we get started, just by a raise of hands, who has actually used the grading optimizer in Civil 3D? Alright, and once. There we go. That's fantastic. Alright, so just to introduce myself, my name is Grieve. I'm currently a civil design technology specialist at Modena AEC, and I have around close to 8 years experience within the civil infrastructure as well as in the construction, specializing within earthworks, road design, as well as the wet services. So looking at the context today, when we look at the grading optimizer, we still have very fundamental AI elements that we are looking to. So starting off with our data collection, making sure that we look at clean, clear data, then the design intent, breaking down the logic of how the AI is going to utilize our design elements within the application model space, and then how they interact with one another. Then the optimization engine itself, so we'll go into a bit of more technical detail, how does it actually function and utilize those elements. And then the AI algorithms, I'm going to try and explain a bit more detail on how we are actually using generative AI in this. So we've been hearing a lot about agentic AI and LLMs, so this time we'll be using generative AI for this. And then how are we actually going to be combining all of these into a solidified, usable workflow. So like Jay mentioned this earlier this morning, data in equals data out. So data clarity, we need to ensure that what we're feeding this model is a representative of the closest element of the site that we are going to be manipulating. So as we start looking at the tools within the grading optimizer, we will see that we have three main elements, starting with the generic layout tools. So with the starting point, you'll see we need to ensure that our ArcGL data from the surveyor or wherever you're getting this information is as true as possible. So as much data as possible from your surveyor is critical. So scoping out the works from the surveyor is going to be detailed, because if you do not have that element, when we go over to the optimization engine, it might actually reduce those sloping levels. Now with the grading optimizer, we are going to be breaking down these elements into algorithms. And this is when we start looking at our first zero elevation geometry. So later on I'll go back onto hallucinations that Jay spoke about. The AI at the moment, especially with generative AI, is if we feed it too much rules and too many design prompts, it doesn't know which one to prioritize. So it starts hallucinating and giving you the answer that it thinks it should be giving you, and not actually processing the prompts that you are providing it. Then, this is where the grading optimization changes a little bit to the normal intent of design. So here we can see with directional control, we will apply a basic XY control, and the software or the grading optimizer will start playing with our Z values. So this is where we'll start applying our minimum and maximum slopes, drainage lines, low points, and so forth, and then the AI will be able to break those down incrementally. So this is just a basic overview of the traditional grading versus the new generative designs. So you will see that we'll look at primary inputs. Previously we had to manually input and assign X, Y, and Z data within the site that you're working with. And that would also take hours. I mean, just doing a geometric road layout can take up to a week. Now with this, we are just speeding up this with the generative tool. So the next thing we need to make sure of is with the processing, we can see that manual iterations, as our engineers start making design changes, site changes are happening on site. Normally you have to sit for a day to update those and update everything that is linked to that initial element. So now with the generative AI, that allows us to start using mathematically driven algorithms to start adjusting these values within the Z value or the elevation points. Then this is where the main target point of the grading optimizer comes in, is with our balancing of our earthworks. Because once we've done our design, we still need to make sure that with regards to quantities as well as costing on this project, we can't be clearing and grabbing a meter. That's just not feasible. So the algorithms once again start utilizing how can I optimize this with the least amount of bulk earthworks that gets me to the best balance. Then with primary use cases, you will see at the bottom, normally we'll have highly detailed final construction models and corridors where the generative AI just allows us to generate a fast, rough iteration, but we can, with a bit of a workflow change, we can actually utilize this for detailed elements. So for example, a good example that I can use is for the fast generation of rough elements. That might be a good overview for your clear and grout, getting a nice baseline started as if you had an excavator on site and just clearing it out for you. And then when we change our workflow a little bit, we can go into the highly detailed elements where you've now designed a parking lot with your curbs, you've got a nice little stormwater channel running down the side, but on the back of that stormwater channel you might have a half-meter height difference. And normally that's where we might spend 2 or 3 hours trying to figure out the right workflow on how we're going to tie these levels in. Now, instead of sitting and doing it yourself, we've got Grading Optimizer for that. So it will actually run thousands of iterations to find the best solutions. And you'll see shortly that it actually works on a reward system. So the closer it gets to a balanced cut and fill, that is seen as a reward, and as soon as it goes past that and goes away from that goal, it sees as a penalty, and that is how the system is able to decide on which is the correct method that we're looking at. So as we start taking these single plane elements, we'll start building them into little blocks and structurizing the model. Because when we start giving too much information to AI, like we said, it can lose it. So these are some of the basic elements that have been brought in with the Grading Optimizer. And each of these is seen as its own tool, and we'll then use the Douglas-Radsford solution to implement each element within the structured input. We then have our gravel pads, so that will be anything specific for our parking areas or anything like that, any flat plane or single slope platform. Our pathways, any walkways or road elements that have not been designed with a facility corridor. Then our building pad, so this is a single elevation element just to make sure that we've got the building outlet footprint for the platform itself. Then smaller elements like the retaining wall. This is what's going to allow us to apply a near vertical drop if you should need that, where we might have a 3 to 5 meter height difference. And then lastly is our ponds, so this is just a depression depth within the surface that allows us to store or retain any liquids. So using the deterministic AI, this is where we are not using agentic AI, but like I said, the generative design. So as we take each of those individual elements, you will see on the right hand side, the algorithms get used or start building onto one another as well within that structure. So within the Grading Optimizer, this is where we start actually looking at the physical tool itself and how we actually start playing and specifying all of these design inputs. So this is typically what you'll see when you load into the application with your model, and we have 3 main controlling elements that we can control apart from the boundary edges like the grading platforms, pathways and so forth. So the main objective of the optimizer is to balance our cuts and fills. So that is what it will prioritize over everything else. And then we can give it secondary objectives from there to define and redefine our elements into a more finite element. So such as minimizing earthworks. So when we balance our cut and fills, how can we reduce the amount of inputs needed to get to that point? So instead of moving 300 cubes, if I just move 50 cubes from the left-hand side of the site to the right-hand side of the site, I'll be able to balance that more efficiently than just doing the entire site as one. And then lastly, this is a very controversial one, especially with civil engineers. I've heard this a lot. Some people like using a smooth surface. It looks prettier, it displays prettier, but out of my personal experience, I'm one of those that actually does not like a smooth surface. The reason for that being is it gives me more detailed views of any discrepancies between model elements. Because if I have a triangulation jump between those elements, I can see that something's not right over there. I do not have a smooth transition or an infill for that element. So use that as you see fit, but my suggestion would be try and reduce that as much as possible just for accuracy. And then lastly, we have the performance toggle, so the refining of the surface. So this is disabling the AI over triangulating the surface. And because we are now working with a generative AI, we still need to bring in the de Launay equation from Civil 3D that is currently in it to make sure that the triangulation that's happening with AI making all of these changes is still feasible and functional within the software. Because it doesn't help this grading optimizer sees the 200 cube difference and it just decides to drop a curve by 20 meters because that's going to solve the solution. That is not feasible, it's not realistic, and that's where the de Launay equation comes back in. So, tracking feasibility. So the proximity measure, as you can see, converges to the next proximal measurement. So what that actually refers to is, as it goes through these iterations, it's using that reward system of positive feedback, negative feedback, to make sure that we get to the intended solution at the end of the day, which is our starting point of the cut and fill balance. Then, as it goes through to the next point, we can actually start tracking it, seeing how the application, through these thousands of iterations that is happening within minutes, is actually showing us these graphs. And we can control this element as we look at the flatlining of this graph. So as you can see, we've got our full value in red, cut in blue, and then we've got this orange line in the middle. And that is actually looking to make sure that as we flatline onto 0, you can decide how long you let the equation run, because there's a point of no return, or it's not feasible to get that final input value. So that will allow us to see at a certain point when you are happy with the flat line, we can then just pause that element and you can then design from there. So the optimization heat map, this is just a nice little visualization if you are starting to work with it and you don't really understand the algorithms at this stage. So as you can see on screen, we've got small elements like our max slope violations, identified in red, and these violations will appear once you have finalized your optimization. So as you're running your iterations and you see that, all right, I've got too many heat maps for maximum slopes, then we go rewrite and let it run further and see what options we get at. You then also have your direction vectors in arrows, so that's more focusing on our stormwater drainage, making sure that obviously the design drains to the correct low point. We have additional vectors such as probe points that we can use as a design tool within the gradient optimizer that allows us to specify where we want to specify a needed low point. So even if your surface does not have a low point there, or it has a high point, we can override it to tell it to make it a low point. So the control that it utilizes is very, very beneficial. Then you can also see we've got minimum slope violations. Majority of the times those aren't too critical, it depends on where it's placed on the site. So that is just a nice design aid in that sense. So understanding the AI integration. So this is where we are starting to look further into utilizing the individual tools in the greater design picture within the workflow that we are applying. So the main thing that these tools are doing is all about efficiency. How can I save you time, and how can I make the design technicalities or difficulties smooth out a lot quicker? So let's have a look at the physical Douglas raster solver. So we've got 2 steps or 3 steps that happen through the Douglas raster. So the first step is where it actually takes down our grading site, our platform, our pond, and our pathway. And it starts on the step 1, and it identifies each tool and assigns them their hierarchy within these calculations. Because, like Jay mentioned earlier, this is where we need to make sure that we don't allow any hallucinations to take place. Because as you are overlapping design inputs, let's say, for example, between your grading site and your gravel pad, those are 2 flat paying elements. Now, which one takes preference? And this is what the composition allows us to do. Then, step 2 is the proximal mapping. So, as we start assigning the structural format of these elements need to start intertwining with one another, and the proximal mapping is what allows us to take the order of operation that has been combined and take the de Launay equation once again on the triangulation of that surface and ensure that you are on the right track. And then lastly, under the iterative refinement, now that we've confirmed that the triangulation is correct, and it is actually a feasible, realistic element. That will now allow us to start our iteration design. So that is where we are now allowing the algorithms to go step by step and run these thousands of iterations at once. Or not at once, but within minutes. So I actually run 3 large models at the moment. The first one, I just tried to do a clear grub. That was a nice quick one in 2 minutes. I then did a bit of a parking lot design with a entrance road, bit of a stormwater channel that led into a pond. That led over to a 5-minute implementation. And then I took one of our old previous projects that we had worked with, where we had a certain section where we had the entrance road coming up, and the building was further down, and we had about a 15-meter height difference between those elements. And we had designed this many years ago, and I thought, let me just see what would it look like if I had grading optimization back then. And what I noticed is, initially, I'm talking about the entire site now, we were close to 2.2 million cubes that had been moved, whether it be cut, filled, imported. And at the end of the day, after running the grading optimizer, I could see that I could have actually reduced that closer to 1.7 or 1.8 million cubes just by identifying where it would better be placed to move that instead of cutting away and refilling it again. And now we just need to start understanding how these XY controls work within the grading optimizer as well. But how does the application actually take those Z values and apply our design inputs to these with regards to our maximum and minimum slopes, our drainage points, whether that be around the pond, through a channel, over a weir, and then finally into the pond, or if we're even doing an underground storage element, we can control those elements and see those from there. So, under the controls, this is where we just understand how the optimizer, once again, just locks our XY positioning controls to make sure that our designs as an engineer does not change, that we're not changing the layout of the parking area or the geometric layout of the road. And that will then allow the application to focus on the elevations. And this is where physically then runs the iterations of, all right, if I move this 2 meters up, what does the model do? Does it increase or decrease mine? Bulk earthworks. Okay, it increases it, that's a penalty. No, lower it. And that's how the thousands of iterations run. So that's why it seems like it goes through 100,000 iterations. It's not actually that it does the entire site at once, it's per point individual iterations. So it does identify specific key points that need to be tied in, and the de Booni equation just makes sure that it smooths that out and makes it realistic again. And then with your results, once again, that just comes back to the de Booni equation. And now I want us to start looking at how do we utilize these tools and augment them into our day-to-day workflows. Because it's one thing to sit and play around with the grading optimizer on a Friday afternoon. No one's looking at you, there's no big stress. However, until you get to your first project, the deadline hits for Friday, and you're like, oh yeah, this doesn't actually work the way I wanted it to. So how do we actually look at that workflow? So as we go into the balancing of this, so as it goes through rapid exploration of design alternatives, it does not allow us to do vertical curves in advanced profile designs. So it will not be able to manipulate any road corridors or any pipe network elements that you apply a vertical curve to. Because remember, we are still working with triangulation. So in order to do that, we will need to ensure that in our surface parameters, we need to look at our tessellation spacing. So just for those that are not aware, tessellation spacing just refers to the distance, the maximum distance allowed between the surface triangle and the defining object. So the smaller we make the value, the more detail we come on. Then from there, it cannot contain a consistent cross slope perpendicular to curving centerlines. So the commonality that you'll see at the moment is curvature. Surfaces and curvature have never really been friends, it's always been a battle, and I'm pretty sure we all understand why. And I don't actually agree with that last input. With the workflow that I had at this stage, it was a factor of does not put perfect models out. I have been able to refine that to make sure that when we load our elements into the grading optimizer, building your tools for your grade, your site limits and stuff like that, break that down into its own separate iterations that you are running. Do one element at a time, and then you will be able to get to your perfect tie-in elements. So once again, looking at not populating too much information at once within the system. Understanding the system's hierarchy and taxonomy will allow us to then highly refine the workflows to get the output that we require. So this is just going to be a basic overview of how we would then generate the surface, we'll extract feature lines, and we can then export those as point groups. And this can be used for contractor data, or if you're working with certain peers that need to be able to build a topo solid within Rivet, we can then provide that data to them raw and dynamic. And then lastly is just covering up the conclusion to looking at the optimized workflow. We will just look at, once again, ensuring that we work with these single tool elements. That then bridges over to the balancing, where the gradient optimization takes over, and then at the end we will then have our human refinement, once again coming back into Jay's point, trust but check. So it might look right, you have this fantastic thing, it's saved you 3 hours now. That would normally put person in complacent situations where you're happy. It looks good, but then you'll actually zoom in and you'll see your parking lot is 3 meters higher than what it's supposed to be. Or the entire model elevation, we're no longer sitting at 1345, but we're sitting at sea level. So just remember to double check those situations. So lastly, your computer is also utilizing hardware and tools. So understand that it can break if you don't have the correct hardware. So please make sure that you are not overloading your systems, because I have heard many case stories, and I've been a problem my child myself, where I had literally burnt out the CPU on the motherboard because I thought I was going to be clever. So just double check for those. Fantastic, guys. Any questions?